many things to be discussed. I don't want to waste your time, and I prefer that we utilize the time as good as we can. So during this lecture time, we are going to have some breaks, so you can go and grab a cup of tea if you want, and come back and moving your legs, because I know that many of you have been sitting in front of the computer for a long time today, either for our sessions or other lectures. Now, the most important thing is today we had the lab sessions. I managed to do the recording, but I brought the wrong camera. I ended up doing things with the laptop camera in the first session, and then I did it with the mobile phone. But you can see that the quality wasn't that good. But I can say it's acceptable, especially for the second recording. Go back to the Canvas page, and I would like you to go to the first I'm going to make it a student view. So this will show me what you can see. So if we're going to go to the modules, and we go back to week number 1, we finish from that. Week number 2, I mentioned last week that I couldn't find the second half of the recording complete, so I have to use the last year recording. So this should work anyway. So we have the lecture divided in 2 halves. I put them on the Bilibili, so the students who are in Asia who have restriction from getting to the YouTube, again, to be able to access to the lecture recording. And also I have the 2 parts uploaded to YouTube for you. Why I prefer the YouTube, not something like just go and watch it through the student SharePoint, because some of the students may prefer to watch the lecture on their mobile device, which is something is going to be actually very hard to be done. Sorry, someone sent me a message. I'll check. So, session. Okay, so I'm accepting this student to share things. Okay, now for the week number 2, if you are going to check the slides, you will see that we discussed the example for the. Okay, I can't see if you can hear me or not. So please just tell me if my voice is clear or not. Can you hear me clearly?
Yeah, I've got you.
Okay, so during the last week's session, we went through the lecture slide, but we had an example about the sieve test that we learned, or we did in the lab today. And actually following the same example is going to be enable you to do the work, but I'm going to make it much easier by give you more examples and even an Excel sheet, the process for the same calculation. I will do that next week, because the today session and the rest of the week we're going to discuss the assignment number 1, because this will be the important one. For the due date, I've been asked today by one of your colleagues if the due date is going to be the same as the end of the week number 4. The answer is no. All the assignments are going to have flexibility with the due date based on your situation, because I know that students are going to have many assignments due on the same date, so I don't want to put too much pressure on you. So we said that the lab session explained in the lecture number 2 for the particle size calculations by using the shaken sieve experiment. We're going to come back to this one later with many examples. Now, the week number 3, which is the lecture, has already been available for you since I think last week, and the recording is going to be available soon. I shared some charts with you, and we're going to use these charts today to do a design procedure for the pins and decoupers, and that's something we're going to talk about in today's session. It's already available in the lecture number 3. Assignment number 1 is available for you right now. The ball circle example is available here again to run another session for the student, because I met some of the students, they told me they never used the software before, they used the AutoCAD or other software. So again, to repeat the process for them, and everyone actually is welcome to attend on how to use the software step by step to make the ball circle calculation, which is actually we're not making something, we're just sketching the line. Sometimes we do it on paper and use the results. Here also we have a tutorial for the assignment number 1 from last year. I will try to repeat the same tutorial today, but it's going to be in a lighter version. And if you need more questions, I'm going to be more than happy to repeat for you anytime in this week. Well, I get to have almost too much free time this week, so I'm going to be as busy as the week after. And of course, I can run the next session, and I think that we should be done. Subject will be earlier. Understand that I'm more than happy to offer the help. Now, we're going to take a look at this one after we finish today's lecture, because the lecture is covering all the questions we have in the assignment number 1. The lab session from previous semesters is already available here, and actually this one is even more detailed than the one we did today, because it's going through the calculation steps as well. And we have some videos here, and you can check these videos if you would like to have more details about the lab work. But now let's focus on the lecture number 3 and the assignment number 1. So before I get to go forward, do you have any questions before we start the lecture? Any questions before we go through the lecture slides? Lecture slide, as you can see here, consists of 120 slides, but definitely we're not going to be so deep with the 120. Most of these 120 pages actually is going to be just describing something that you may know already, or we only need to talk about it officially. It doesn't have to be into deep. So I will go with these slides and take a look behind the lecture. Switch to another screen. So I'm going to stop the sharing for a while and reshare it once again, because the screen that the presentation showed up is the third screen. Okay, now I think you can see the screen. Okay, so briefly to give you an introduction about what we are going to cover today is going to be the storage system and the material handling system in general. We talked briefly in the week number 1 that we need to extract the material, transport the material, and have a buffer storage for this material, or semi-permanent storage. Now, when I said there's no permanent storage, of course, there's buffer one, when again to leave it for a while, something like you are going to change it from the ship to the train, or from the train to the trucks. So usually what we do is we take it from the train to the silo, store it for a few days. For example, we're going to fill the silo and have a certain amount of storage somewhere near the harbor until we are going to fill it, and then the ship arrives and we are going to empty the silo to the ship. Okay, so that's the main goal of having the silo and the bins and the hoopers. And that's what we're going to describe today. And we're going to end up with knowing how to do the basic calculations for designing all the silos, and the basic calculation, actually it's more advanced calculation on how to design the bins and the hoopers. Mainly, again, to depend on the results we got from the shear test experiment we learned last week. We got the Junkies shear test, and we learned it in lab today. So this construction is called the silos. You can see that we have a metal shape metal structure silos, and we have the concrete one we call the tower silo, and these are smaller size metal or stainless steel silos. The concept is going to be very easy. We just fill them from the top, as you can see here. Okay, so the trucks are coming or the trains are coming and start to fill the silo for the storage. This can be a strategic storage. For example, we have, let's say that Australia, for example, have the wheat. That will be storage which is going to be enough to feed the whole country for the next 6 months. Okay. Now, usually when it's going to be for 6 months, because they're not going to keep the material inside the silo for 6 months. They start to use it and replace it continuously. So we fill it from the top, and the most important thing is to empty it. We don't want to have the material here all the time. Now just imagine, you learn something in the fluid dynamics that the head of the pressure is going to cause more forces at the bottom, right? So if I get to have a tank of water, just imagine that this is a tank of water. Of course, if I get to add a level of the water to this height, the pressure at the top is going to be low, but the pressure at the bottom is going to be high. And that's not something similar to the example we talked about earlier. It's not a pressurized. The pressure is going to be due to the weight. So the highest head of the pressure is going to cause higher pressure at the bottom. Now the same thing is happening with the dry material. Imagine that we are going to have a wheat here. So if you are going to, well, actually, once I saw a movie, I'm going to show it to you later on a person who trapped inside the silo, then he being swallowed by the wheat. So don't do that in the future. But it was a movie anyway. So the pressure that we're going to have at the bottom is going to be much higher than the one we're going to have at the top. We learned last week that when we're going to add in material, we're going to have some cavities between the particles. And these cavities are actually going to affect the amount of the density we have for this material. So what's happening is that within the time, the materials start to push each other downward, compress the material, increase the density, close the gap. Now, even worse, that the friction between the particles is going to be higher. The changes in the density will also going to increase the friction between the material and the wall. When we fill the silo is going to be easy process, but when we empty it, it's going to be the most important process. We want it to be empty, fast, easy, not damaging everything, not the material, nor the silo itself. And that's what we're going to learn about today. So in general, we learned last week that we have two types of the storage. This can be just the outdoor storage, which can be open to the air. Sometimes they're putting just a cover on the top of it to prevent it from drafting. And we have the confined storage, which can be the closed one. So for the outdoor storage, where the coarse material are going to be stored on the air, we can put in large piles, and 100,000 of tons of material is going to be involved. It's going to be very rarely to be affected by the wind or by the rain. The which something can be affected by the environmental problems such as dusting or leaching suitable for the material cooling piles, and the dusting control is going to be done by covering the piles, and this will solve the problem. And leaching can be controlled by covering or by simply locating it in a shallow basin, so it's not going to be flowed from the sides. And we have some cold storage, so you can simply just pile it, and we can build a wall on the side, and this will prevent the material from flowing to the outside. The same thing can be done for the sand and the gravel, because it's not going to be a problem. Now on the other side, if I'm going to have the cement powder, I cannot store it on an open or outdoor storage. In that case, I'm going to use the confined storage. And this can have different sizes. The small one is going to be called the bins. The large one is going to be called the silo. But in general, you can see that the silo and the bins are almost the same. The only difference is that for the bins, it's going to have this device at the bottom, which called the hooper. Okay, the hooper. The hooper is going to contain the opening at the bottom for the emptying of the pins or the vertical silo. Now this is silo, and we call this one is the flat bottom silo. The bottom is going to be flat, but we are going to have something called the moving ground, or the usually they call it moving ground, or they call it shaking ground, or live ground. That's going to have multiple screws. Okay, and this will go to ease the process of the emptying of the flat bottom silos. Later this week, I'm going to post a video just for the process. We call it, actually, it's not going to be an equipment. We call it accessories to empty the pins and the hoopers with the aid rather than the gravity. Usually this device, the hooper, is going to empty the tank due to the gravity, and of course we're going to have more head. The gravity is going to be easier to be pushing the materials. So you can see that we have different types that the storage can come in all shapes and sizes. This one is the square one. The other one we saw, which was the cylindrical one, what we call the conical hoopers, and we have the pyramidal shape as well. We have the wedge hoopers, which are going to be a long, and at the bottom we're going to have the two parts are going to be connected, and the outlet is going to have rectangular shape instead of the square shape. We have the chisel hoopers, we have some with the transition hoopers, and we have some with two instead of one outlet. Some of them, of course, get to have single outlet, and I think that you saw that in the cement silo or the grain silo they use towed by the trucks. Now, the storage for the bulk cell is very important. We're using the pins and the hoopers, which are very common application for storing the material as a buffer storage during the material handling processes. The hooper, as we mentioned once again, is going to be the taper shape or taper section at the bottom of the pin, and this contains the opening. It's always going to found above the feeders, by the feeders device that feeding the process in the material handling process or any manufacturing processes, and it's going to use the gravity to reclaim the stop lines. Now, both the pins and the hoopers must be designed for the actual bulk materials being handled over the entire range of the operating conditions, including varying characteristics. Because we said that we add the material on the first day, after the second day, the characteristic will be changed, including the density, because we said the material will be simply compressed down, and thus we are going to change its density. Hoopers must be designed so they're going to be easy to load, and this is the easiest part. But the most important things they should be designed so they're going to be easy to upload. We don't want to leave any materials inside. Some of these systems has been designed wrongfully, and this will cause either collapse of the system or even that the material inside is going to be caked, and it's going to be impossible to empty from the or unload from the silo, and thus you spend thousands of dollars, and for the big silos maybe hundred or tens of millions of dollars, and then you have to leave it because it's not going to be useful. Now, for these silos, is something similar to the pins, but it's going to be a larger structure. Usually, it's going to have a cylindrical shape, a high height, and it can storing any bulk materials like the grain, the coal, the cement, and the food products. The silo is going to be usually tall, relatively it's going to have a small diameter, which is going to be used for the pin storage. Types of the silo, and the most common one, and I think that you saw something similar to this tower silo when you cross the Zaka Bridge, and the one actually we see there is for the storage of the grains. Mainly it's for the wheat, and the structure is going to be made either by concrete or stainless steel. Some of them is going to have the low oxygen tower silos, and this is very important to stop the fermentation of the material we have inside. This will be very useful in the case of storing the grain for a long time. Of course, it's going to be sealed like this one. The concrete is going to be very small porosity, so it's not going to allow it's going to allow the negative pressure inside the silo. The other type is going to be called the bunker silos. Now the bunker silos, as you can see, is going to be an open type. It can be covered temporarily just to save the material. It's going to have wall on the side where you put the materials as piles, and then we can cover it with either this type of cover, which is semi-solid, or sometimes they're just putting the plastic bag on top of it and using something similar to the tires as a way to prevent the air drafting. The other types of the silo we have is going to be the cement storage silo. Now these are going to be specialized for storing the cement. Storing the cement is a very critical process because we need to have zero humidity inside. So once again, this can be also have very high observability in it. And usually the process of emptying this one is by sending the pressure through this pipe, okay, sending the pressure, pressurize the system, and this will cause the silo to be emptied. I think that many of you saw the similar silos. Once again, if you go near the fish market, you can see there was a construction site there, and they have a concrete factory mixing the sand and gravel and the cement to make the concrete mixture and send it through the mixer truck, and it's going to be used directly for the casting process. Now, also we can have a temporarily silos, like the bag silos. Now, the bag silos, as you can see here, is going to be actually type of the polymers. They start to fill the silo in the spot, okay, and then they're going to empty it. Usually we're using this type of the silo during the harvesting process because the process of the harvesting required to fill the trucks. Sometimes there will not going to be a sufficient number of trucks during the harvesting season. So what you need to do is that use the trucks, fill the trucks, and you send the trucks to be emptied in the storage area, or filling the train trucks to send it to the silos, and you're waiting for them to come back. So you don't want to keep the things in an open air, so we put it inside the bags, and this will be a temporary storage system. But it's still in use, and it's very popular. Now, once again, the silo can be classified according to the material we use to build them. Steel, iron, galvanized steel. This can have cylindrical shape, it can have conical bottom, and so on. We have some special solution like this equipment, which are going to be used to fill or empty the silos. Okay, that's what we call it actually. Here we're going to have something like this screw, and this screw is going to be sending material by the movement of this motor at the top, and then it's going to be used to fill the trucks. We usually going to have a side outlet to relieve the pressure, or to use just gravity to empty the silo instead of using the other types of the equipment. Well, now we have multiple storage systems. So actually what's happened here that we are going to fill the tanks from one source, and we can empty it from multiple outlets. Well, we're talking here about, well, actually what I would like to show you here is that software which can help you to design the equipment and the silos. It's very important. You're going to select the materials, you're going to select the accessories you're going to use with. This can also help you to design the structure in case you're not going to have the flat bottom type of silos like this one. So this one is going to have the lower silo, which is going to have structure on the side to support it, and for the larger size, we're going to use the platform silo. The construction of the silo and how they make it. Actually, I posted a video on that yesterday on Teams. Usually, they're going to make the sheet first, galvanized one, so they're going to be rusted, and then they start to build the silo. Building the silo process is going to be by the installation of the roof first, assembly of the roof first, and then they start to take it up step by step. So take it up and add another layer, take it up and another layer until we're going to have the required height. So something like if you ever seen how they install the crane, actually the crane is also do the same thing. So you make the T section at the top first. Okay, and the control room is going to be on the floor at the beginning. They lift it up and put the lower structure. Take it to another height until we get to reach the final height. Now we go to the bin storage once again. These are temporary storages. This type of the storage is going to be used for the shorter time of the storing, and it's going to be used to feed an operation or feed the process. So this, for example, can be connected to feed the medication mixture to the packing system. Okay, that's very small type. The bin typically much shorter than the silo, of course, and typically is going to be used for holding the dry matter, such as the powder or the grain. The bins may have a round shape, like the photo below, or the square shape, like the one above. The round bins usually tend to be empty more easily because we don't have the edges which can have a double refraction area. The stored material may be a powder, as we mentioned earlier, or it can be seed kernels or any popcorn or dairy material that required to be dry most of the time. Now, when we are going to talk about the bin, that's the bin at the top. Okay, the below down here is what we call the hooper. So the hooper is the small vessels at the bottom with a sloping bottom for the temporary storage before the feeding of the soil to the process. You can see is the hooper can have different shapes. A conical one, and this is the cylindrical type. So it is going to have, for the opening, is going to have a height and length, and we are going to learn the design of this type of the outlet in today's session. So it's going to be as easy as feeding from the top and emptying from the bottom. The hooper can be vibrated for extremely encouraging the flow. The hoopers can be used individually with no need of having the pin at the top. If we're going to have it as a pin at the top, that's when we use it for the storage. But if we're going to use it as a hooper alone, it's going to be temporary storage, and it's going to be used to feed the material to the processes. The angle of the sloping sides usually is going to be more than the angle of the repose for the material we have. Otherwise, it is going to be less, the material will stuck. So actually what we do is we're increasing this angle, and this one encourages the material to flow to the gravity. Otherwise, if it's going to be flattened because the angle is going to be quite low, the material will stuck in the top. Now, once again, the designing of the opening here will be different from one material to another, and of course going to be larger if we are going to have a longer storage time. So I think now we finished the section number 1 of today's lecture. I will go for the next stage, which is going to be the hooper design and the hooper design background first. So I think that you went to some areas around the New South Wales, for example, or the countryside, and you saw something like these small towers. These were the old bins that been used by the farmers in the agriculture. Before 1950, the design of the bins and the hoopers was done by architectural shape. So they used to make it nice looking, but nobody thought about how to make it more efficient. The result was what we see in the photo below. Due to the wrong design, things was collapsing. So once again, Genki developed the theory, the methods to apply for the design process. Yes, the same person who found the process of the testing of the internal shear for the material and the internal or the shear between the material and the walls that we learned in the lab today. So simply he related the material stored in the design of the pins, the hoopers, and the silo. And he set the equation and the measurement for the particle properties, and he made many charts and tables which can be used for the design procedure. Once again, this is another example for the old design. They just wanted to have a nice shape, but they didn't have the real calculation for the process. And it's all end up with failure. So Karl Jacob had set a design questions for every designer for the pins and the hoopers and silos. The most important one, we said that we need to design the pins and the hoopers and the silos to be easy to be filled and easy to be emptied. The hooper will simply begin to allow the process of easing the emptying process. So the question that's been set by Karl Jacob on the design procedure for the pins and the hoopers were, first, what is the appropriate flow mode we need? You remember that we have basically different types of flow modes, and we discussed that last week, and we're going to have a look on that at the moment, next. Also, what the hooper angle we need. I think that we have the two answers for that one now, because the answer for the first one, it should be the massive flow. Massive flow. That means the whole material we're going to have inside the hooper is going to be moved at the same time, and thus we're going to have a constant emptying for the hooper. What the hooper angle, we said this should be more than the angle of repose of the material. But you will find out that actually the angle of the repose is rarely used in the design procedure for the pins and the hoopers. Now, the other question is how large the outlet for reliable flow. That's what we're going to learn today, how to calculate the minimum diameter and the equivalent dimension. We're going to have the rectangular outlet for the pin outlet. What type of the discharge is going to be required, and what is the discharge rate you are going to need? So we're going to answer all these questions in the next following pages. So once again, if we're going to design the hooper without consideration of the actual material being handled, we're going to have a real problem. So I cannot design a hooper to store the wheat, and then I'm going to use it to store, for example, the sand. Okay. Now, even if I'm going to have the whole wheat, maybe I can use it for the barley. That's because it can have almost the same characteristics. But I cannot use it for the broken wheat, because it's going to be totally different. The material is going to have the internal locking properties that's going to change the flow pattern. So for many materials, the flow problem can be eliminated if we're going to ensuring that the massive flow pattern is going to exist in the vessel. The massive flow pattern, once again, just to remind you, is just imagine that we have a water bottle, plastic one, and I'm going to flip it in the back, and this tab is opening. So the whole level is going to go down at the same time because it's a fluid. Now try to do the same thing. Get a plastic bottle and try to put in it some rice and flip it and see if the material is going to flow at constant rate, or you're going to have some material to slow down on the side. If we're going to have the whole system going down at the same time, this will be good. But if we're going to have the material moving just in the middle and we have a stagnation on the side, this will be a problem. So the first step to achieving the massive flow is to ensure that the converging walls are going to be steep enough, and also going to have a low friction with the materials. And this will allow the bulk materials to slide along them without any serious resistance. This should be done first by doing the testing of the material to measure the friction, the wall of friction with the material, and then calculating the minimum Hooper angle that will be along massive flow. That's what we learned today. We learned about the wall of the material friction, the internal material friction, and we learned about the wall friction of the material. And in today's examples, we're going to learn how to calculate the minimum Hooper angle and also the outlet diameters. So let's have a look about the different types of the Hooper flow modes. The main three modes of the flow are the massive flow I just described, we have the funnel flow, and we have the expanded flow. So let's have a look about the three different types. So the first one we have on the left is the desirable one. We're always looking for the massive flow. You can see that the massive flow, the material at any position in this solid system is going to be moving at the same time. No slowing down, no stick and CNDB happening on the side. Now for the funnel flow, because the funnel flow we're going to have the moving of the materials only in the center. So the center is going down